So this video is extremely important for understanding trig functions. So when I first introduced trig, I talked about where sine, cosine, and tan come from. I showed you the cosine, sine, and trig tables. I showed you or explained how a calculator works. So that's really important to understand where trigonometry comes from. But now we're going to extend those trig ratios to trigonometric functions. So in the previous video, I looked at angles greater than 90 degrees, and that's kind of what I'm going to extend from here. I'm going to draw those angles, on the Cartesian plane and show you the relationship between the trig ratios and these angles on the Cartesian plane. And if you really understand this, and then you understand SOHCAHTOA, Pythagorean theorem, and the special triangles, that's really all you need to know for any question related to trig ratios and trig functions. So it starts like this. Imagine I have a point on the Cartesian plane, and at that point, I'm going to draw a terminal arm that extends to that point. And again, you can imagine that this terminal arm has rotated that angle, principal angle theta. I'm going to set up the right angle triangle for this principal angle. And so the distance from here to here would be the x value of the coordinate, and the distance from upwards would be the y value of the coordinate. And of course, this is the radius of the circle. If we imagine this terminal arm rotating around, that would be the radius of the circle. So I'm going to set up the trig ratios for this right angle triangle. So I'm going to do SOHCAHTOA. I'm going to start with cosine of this principal angle. So cosine is a measure of the adjacent and the hypotenuse. And so here's the adjacent and there's the hypotenuse. So it's a measure of the x value to the ratio of the radius. Then I'll do the sine ratio. So sine of theta is a measure of y to the radius because sine is opposite over hypotenuse. There's the opposite, and there's the hypotenuse, so y over r. And tan of theta is the opposite over the adjacent. So here's the opposite, and here's the adjacent. So tan of theta is a measure of y over x. So these are essentially functions because the radius is going to be some sort of known value. Like you'll have a radius of a circle, it'll be a numerical amount. And what changes as we go around this circle are the x values change and the measures of theta change. Likewise, for the sine ratio, as I travel around the circle, the radius is staying constant, so the radius would just be a number, but the y values are changing with respect to the angle that I've rotated around the circle. And likewise, the tan ratio, now this one's interesting. If I rotate a certain number of degrees, it's a ratio of these two things that are changing together. So this kind of has three variables involved. Theta is changing with the y value and also the x value. But this is really important, and that I can apply those trig functions or those trig ratios to angles on the Cartesian plane. Now I've shown you an acute triangle right now. I'm going to show you with an angle that's greater than 90 degrees. But before I do that, in each of these ratios, I'd like to show what happens if I isolate for the x and y values. So if I multiply out by r, that tells me the x value of any coordinate is given by the radius times cosine of the angle that I've traveled around. And likewise, if I multiply out the radius here, y is equal to r times the sine that I've traveled. So essentially this coordinate right here, this xy coordinate, comes from taking the cosine of theta times the radius, and the radius times sine of theta gives you the y value. So that's important here. And I'm going to show that again, but I'm going to now rotate. I'm going to go to a point in the second quadrant here. And again, I'm going to do a terminal arm to there, which means that this is my principal angle theta. And we saw previous that if we're going to use SOHCAHTOA in context of an angle greater than 90, I need to draw the related acute triangle. So That would be this one right here, and this would be my related acute. So what I'm going to do is, again, set up my ratios. This would be x, and this would be the y value of my coordinate, and again, this is the radius of my motion. So this is rotating. Imagine that's rotating around a circle. So that's the radius of my motion. If I set up the trig ratios again, cosine of theta is adjacent over hypotenuse. So adjacent over hypotenuse is x over r. Sine of theta is opposite over hypotenuse, y over r. And tan of theta is the opposite over adjacent, which is y over x. Now, I should go back and say, okay, well, wait a second, that's not theta, that's dealing with the ratios in here. So how do I relate beta and theta together? How can I, because I really want to know what the measure of theta is. Well, first things first, I set up these three ratios. I could use any of these to solve if I wanted to solve for theta. If I had the measure of x and r, I could find out what beta is. And then I could use that piece of information to figure out what my principal angle is. So if we can figure out what beta is, then I know that theta would be 180 degrees, because this whole thing is 180 degrees. If I subtract beta, I'm going to be left with my theta. So these ratios are helpful for determining the values of principal angles that are greater than 90 degrees. But I also want to show you that as we go around the circle, I'm going to show you, we're going to keep that same, so I have a point there, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, here. There's that same terminal arm in the first quadrant. Here's the terminal arm in the second quadrant. 1, 2, 3, 4, 5, 1, 2, 3, 4. Here it is down here. And 2, 3, 4, 5. Here it is over here. So the point here, we showed that the x value comes from r times cosine of theta and r times sine of theta. That gives you the x value and the y value of the coordinate. Now you can imagine if I rotate that same terminal arm over here, these are all the same measure. If I go over here, these are the exact same right angle triangles. They're no different. So the measure of x here is the same as the measure of x here, except for it's a negative value, and that's a positive value. So over here, if I isolate for r, x is equal to r times cos of beta, I know that this has to be the same. Let's go with r times sine of beta. I know that these two things have to be the same because the y value here, which is r times sine of theta, has to be the exact same as the y value over here because I have the exact same triangle. And so I have the same measurement on this side, which would be r times cosine of, and instead of beta, I can just say theta, because it's going to be the exact same value as this, except for it's going to be the opposite sign, because in here I have a negative x and in here I have a positive x. But the y value is going to be the same, r times sine of theta. That's going to be the same over here. Now if I go down to this triangle, the x value is still negative, but the y value is negative. So this coordinate here is going to be again, the exact same coordinate as what's here, except for the signs are going to be different. So this would be negative r cos of theta and negative r sine of theta, which means the opposite sign. I'd be multiplying both of these by -1. And then if I go in this quadrant, the y is negative, but the x is positive. So the r times the cosine of theta is the same as the x value here because it's the same x value, but the y value, that's very sloppy, the y value is negative. So these x and y values are just repeating around the circle, and you notice that I don't have to use the related acute necessarily. I can also show that since the x value over here is the same as the x value over here, which is a measure using the principal angle theta here, that if I extended my terminal arm to being This angle, I'm going to get the exact same values by doing r times, again, the principal angle here, which is, you notice, if this is the principal angle here, then beta is the same as that principal angle, is the same as that principal angle, is the same. So it's true that in all of these, the related acute, so that's why I can interchange that theta and not write beta, because if I think about the right angle triangle in the first quadrant, it just repeats itself around the circle. So this is very theoretical. I haven't used angles. I'm going to put this into context with numbers, but that's really what I want you to remember, is that a point on a circle centered at 0, 0 and with a radius of r, those x and y values are given by the radius times cos theta and the radius times sine theta. And that's just based on this. So this doesn't need to be memorized, and either does this. You do not need to memorize that. I just want you to understand that the trig ratios are measures of the x and y values around this circle with a radius of r. And this is where trig functions start. Now I'm going to go into the specific trig functions of sine, cos, and tan with a radius of 1. So that's where we get the most basic sine, cos, and tan functions. I'm going to show you that in the next video. So nothing needs to be memorized here. Just understanding how, we take a terminal arm and rotate it around the circle, and how we use that right angle triangle and the related acute to calculate angles around the circle and those ratios or x value and y values around the circle.